Ladies and gentlemen, today we are going to be looking over hydrogen nuclear magnetic resonance, also known as NMR. Now, there are essentially two different ways we need to be able to interpret NMR because we're going to get two different types of questions being asked for NMR. The first thing that we'll see is we'll have this kind of axis here. This figure, it goes from 0 on the right to 12 on the left. We need to know as far as 12. Okay, and just to label which side is which, we call the right side upfield, and we call the left side downfield. I also have them labeled as shielded and de-shielded. So let's talk about that. And the shielding versus de-shielding, that is what puts each molecule in its upfield or downfield position. So what is shielding? And now, just with NMR, I want to emphasize that we are focusing on the hydrogens. We are focusing on the hydrogens. So what is shielding? Shielding is referring to the electron density. So the electrons surrounding the hydrogens provide a, quote, shield. If this hydrogen here, or if any hydrogen is attached to an alkane, so this example on the right, this hydrogen attached to an alkane, does not have any atoms that are going to withdraw electrons from it. There aren't any oxygens, there aren't any nitrogens, any fluorines attached to it that are going to withdraw those electrons away. So the hydrogen here on the alkane is going to retain all of its electrons. It's going to retain its electron density and is therefore going to be shielded. This hydrogen is therefore shielded. Now, on the opposite side of the spectrum here, we have a hydrogen attached to a carboxylic acid. And now this hydrogen is significantly de-shielded for a couple of reasons. One, there's resonance. The resonance makes it easier for the electrons to flow back and forth. So the electrons can switch positions, as we all know, due to resonance. And that's one reason why. The other reason why is because of these electron withdrawing groups. These oxygens are going to be, they are very electronegative, so they're going to be withdrawing the electrons away from the hydrogen. So the electrons are going to be flowing away from the hydrogen, so that hydrogen is very de-shielded. Okay, so that's what we mean between shielding and de-shielding. And then, like we mentioned earlier, we have upfield on the right and downfield on the left. And if it kind of helps to think about it, if we're at war or something with swords and spears and bows and arrows and stuff, if you're upfield, you're gonna want to put up your shield. If you're downfield, you can relax. You can de-shield. Okay, and I put these molecules specifically on here because we actually need to memorize these three on the left. So on the leftmost part, the most downfield, we have carboxylic acid, which ranges from the 10 to 12 range. And then next to it, we have the hydrogen attached to an aldehyde that goes from the 9 to 10 range. And then we also need to memorize aromatic hydrogens or hydrogens attached to a benzene. That goes from 7 to 8. And then we don't need to memorize anything specifically in this region here, but generally speaking, we have alkanes on the right. And you can kind of determine where they're going to be on the field depending on their level of shielding. And oftentimes, with multiple choice answers, they're going to ask you to compare between different molecules depending on where a signal is on the NMR graph here. So let's look at the actual signals now and how the heck this works. So we have a lot of spikes here, and we have this example molecule up top. So once again, we want to focus on the hydrogens. The hydrogens give off signals. So this red group of hydrogens are giving off the red signal, the blue group of hydrogens giving off the blue signal, and the green group of hydrogens giving off the green signal. Okay, now one question you might be asking is, okay, there are multiple red groups and multiple blue groups. So and we'll go into a little more detail about this later, but because there's symmetry, these groups are actually producing individual signals, but they're just the same exact signal. So they're effectively overlapping here. Same with the blues. The blues have the same exact signal due to symmetry, so they're overlapping. Okay, now let's talk about more specifically how these signals work, specifically the number of spikes. So how do we determine the number of spikes? The number of spikes is determined using the n plus 1 rule. So n plus 1, and this is going to turn into the number of spikes. Okay, well, what the heck is n? N equals the number of adjacent hydrogens. It's the number of adjacent hydrogens. We could also call them hydrogen neighbors. So if we're looking back at this red group has 1, 2 adjacent hydrogens, 2 hydrogen neighbors. So the n for that equation would be 2, and then you always add plus 1, and that equals 3, which is why the red produces 1, 2, 3 spikes. Okay, now let's do the green. So the green right here has 1, 2, 3, 4 hydrogen neighbors. So that's 4 for the n plus 1, and that is equal to 5. So that's going to be 1, 2, 3, 4, 5 spikes. 5 spikes for green. Okay, and you guys can do blue on your own. Look at how many neighbors there are and the number of spikes. And the last thing we need to go over is it's called integration number. Okay, so the integration number, actually, let me step back a little bit. The number of spikes tells you about the neighbors. Okay, so just to recall, the number of spikes tells us how many hydrogen neighbors there are. The integration number tells us about how many hydrogens are actually giving off the signal. Okay, so as we talked about earlier, in this red signal here, there's actually 6 hydrogens giving off the signal because of that symmetry. So the integration number for red is going to be 6. The integration number for green is 2. And the integration number for blue is 4. Okay, so just to reiterate the signals, so we determine the number of spikes, like red, for example, the number of spikes is 3. We determine that using the hydrogen neighbors. Okay, so the number of spikes is about the hydrogen neighbors, and then the integration number, which we'll see below, the integration number, let me write that down actually. The integration number, you're going to see underneath the signal there, and that tells us about the hydrogens giving off the signal. Leave a comment down below. Tell me what you guys think. Subscribe, like, all of the above. Hit the bell or whatever that thing is. Tell me what you think.